Hello and welcome back to the Data Center Power channel. I'm Emma Strutton, I'm head of channels at DCD, and it's an absolute pleasure to introduce this next episode on powering the AI factory, the grid to chip journey. And thank you so much to Schneider Electric for partnering with us on this episode. So with me here today, I have Stephen Carlini, who is the Chief Advocate for AI and Data Centers at Schneider Electric. So thanks for joining me, Stephen. How are you?
Great, great, very happy to be here.
Very happy to have you. Manav Patel, who is the VP for Strategy and Business Transformation, also at Schneider Electric. So thanks for joining me, Manav. How are you?
I'm doing great. Thank you, Emma.
Thank you. And Mazen Zain, who is the VP for New Energies and Global Partnerships at Schneider Electric. So thanks for joining me today, Mazen.
Great. Thanks, Emma, for hosting us. Happy
Oh,
to be
thank
here.
you very much for joining me. So, to kind of get us straight into the conversation, this discussion is all around the grid to chip journey. So, to set the scene a little bit, I'd like to kind of turn it over to you if that's okay, Stephen. So, we're hearing the phrase grid to chip a lot in the industry, but what does this actually mean in the context of data center power? If you're able to set the scene for us a little bit.
Sure. So what that means is taking the electricity all the way from where it's generated, which is the power station on the grid, all the way to the actual GPUs or CPUs in the server. So it's one continuous electrical connection, but it starts off as high voltage, then it's transformed to medium voltage, and that's really where we see the data center or the building coming in, where medium voltage, which is 10,000 volts to 39,000 volts, and taking that voltage, bringing it down to low voltage, and then low voltage, bringing it to the room, which is usually around 400 volts, bringing it to the servers, which is around 56 to 60 volts, and then down to 5 to 12 volts for the servers. So within that powertrain, the powertrain is continuous and it's only as reliable or available as its weakest component. So starting at the medium voltage, you see components like switch gear, you see breakers, you see busway, you see transformers, you see UPS systems, you see power distribution units. All of those have to operate in one continuous powertrain that we call it. And we are managing every point of that powertrain. For example, we're monitoring the breakers to see if they're getting close to capacity or could trip. We're monitoring the transformers to see if they have some rising heat and are going to fail. So it's a very, very sophisticated and uh, resilient system. And data centers, as you know, are not happy when they go down. So you have to maintain continuous power from the grid all the way to the chip to keep the data centers operational.
Yeah, absolutely. Makes sense. And, as well, we've moved from traditional data centers to kind of what has been described as AI factories. But what fundamentally differentiates an AI factory from more traditional digital infrastructure?
So for decades and decades, we had what we call enterprise or cloud-based data centers, and these were based on x86 server architecture, little pizza box servers, and there was thousands and thousands of those servers, and each rack of those servers had 5 to 15 kilowatts of power. An AI factory turns that on its head, and the latest uh, servers, which are the Vera Rubin servers from NVIDIA, those are up to 227 kilowatts per rack. So you go from something 10 to 227. You could see there's going to be many more servers in the traditional, where you used to have like viewing areas and balconies to look over these rows and rows of servers. Now the IT section of the data center is going to be very small. It's going to be very, very power dense. So you have little room for the IT space, but you have lots of room for the power systems like the generators, the switch gear, the UPS systems, the transformers. So you have a lot more equipment outside of the data center white space, and the data center white space is very, very uh, densified. So getting the power to the servers is, through copper, through the powertrain. So it's becoming more and more difficult to get the power from the grid to the chip in the new AI factories. And the AI factories are putting a lot of strain on the entire data center process. So designing a data center with that extreme density is very, very difficult. And the fact that these densities are increasing, every year the densities are increasing. In the past, they were very slow and it's kind of stagnant, but now you have to have a new design every year. And you want to design these digitally before you deploy them digitally in the field. So you want to run simulation software. So the higher density, the more simulations you want to do to see what the impact of different events are going to be on your architecture. Operating these is also becoming very, very critical because you're running at these extreme power densities. You go into an overheat if you have a failure mode, very, very quickly, almost instantaneously. So you have to operate these. You have to have pre-warning of when things are going to fail, and then maintaining them using sophisticated software to figure out when and how the best options are to bring people in and do maintenance on the equipment.
Yeah, makes sense. Thank you. Thanks, Stephen. And why is an integrated approach to power management becoming so critical in these AI environments that you've just outlined? For example, how do prefabricated power modules help operators overcome supply chain realities when there is just such a demand for speed to market? Maybe Manav, if I could go to you for this one.
Yeah, thanks for the question, Emma. I'll reiterate a couple of things, right, which Steve mentioned. So we are in once in a generation shift driven from these AI factories, AI infrastructure, right? So reiterating the rack densities from the past used to be like 5 and 10 kilowatt. A couple of years back, they moved to 30 and 100 kilowatt. And now we are hearing, rack densities move over a megawatt. Now, what that does is it's a full redesign of the power and the thermal architecture. And you kind of think about it like a lot of these AI factories, they consume power as much as a small city would consume, right? So what this does is this infrastructure is a strategic bottleneck, and anything that can be done to deploy infrastructure faster is a key enabler. Now, from Schneider's approach, if you think about the powertrain, the way we look at it is essentially four layers. Layer number one is medium voltage. Layer number two is low voltage. Layer number three is UPS, and layer number four is energy storage. Right. So in any data center, you typically have four. In some hyperscalers, you may have a fifth layer, which is the high voltage line. Now, what happens is if a customer is trying to deploy or a hyperscaler is trying to deploy a data center in North America or South America or other parts of the countries or the world, the grid standards, the safety codes, the project requirements, they are different. Now, where Schneider is really strong is that Schneider is the only global company which can help customers to deploy these data centers at scale, right? So we can guarantee performance from one architecture, one engineering model, performance guarantee, and which is globally consistent while being locally compliant. That is where the prefabrication business comes in really strategic, right? So the time to power is a key strategic advantage for any of the data center operators, right? So in market reality, right, we're looking at 12 to 24 months to energize the hyperscale capacity. And with the current supply chain, the power infrastructure, it presents the most critical path. To address that, we have a prefabrication business called Modular Power Skids. Essentially, we fully integrate and factory build the four layers which I discussed, right? Medium voltage, low voltage, UPS, and batteries within one pre-tested, assembled, wired, and commissioned form factor. Now, what that does is it shifts the on-site assembly to more of a factory integration, the impact being that you can shave off weeks and months from your standard lead times. You also have higher quality and lower variability in the field. This also provides, apart from the lead time, the repeatability aspect, This also is a more safer way to deploy infrastructure at scale, right? It is known that the highest risk, our flash risk, happens during the first energization. So in addition to not assembling, testing, right, we also certify our products. They're pre-certified, pre-labeled to be NFPA compliant. And what that means is, in addition to the faster deployment, we can even deploy these in a safer manner, right? So the key messaging right here being is that the repeatable modules through the modular data centers can help scale fast and consistently in a safer environment.
Fantastic. Thank you, Manav. And when it comes as well to accelerating that time to power and that kind of speed to market, how are standardized reference architectures becoming so important to these AI data centers, particularly around those NVIDIA-based deployments that you mentioned earlier, Steve? And so maybe I can go to you for this question.
Sure, sure. The reference architectures are extremely important because they give you a complete list of all the bills of materials of what you're going to need to support the different deployments. Say you're on allocation for, you could be getting some Grace Hoppers, some Blackwell Ultras, or even Vera Rubins. The reference architectures give you the exact design from a component level that you're going to need, and it also gives you the performance specifications. So you can take that initial design that'll give you all the components, it'll give you spatial layouts, it'll give you performance specifications on that data center, and then you could start uh, looking at your schedules and procuring the equipment. We release these 6 months in advance to when the actual design, NVIDIA generations of GPUs start shipping. So we released the Vera Rubin GPU reference design a few months ago, and it will start shipping a few months from now. So you could start preparing, you could use that design, you could start tweaking the design if you want more redundancy, less redundancy, more runtime. If you want to prefab certain areas, like if you want to prefab the IT room or the powertrain that we were just mentioning, you could use that as part of the reference architecture. But our customers, the data center operators, don't really have the relationship that we don't have. So they don't need the exact data center designs that they're going to need. So we provide that to our customers well in advance so they could start preparing. So when the GPUs arrive, or the NVL72s, the integrated systems arrive from NVIDIA, they're ready for deployment, and the speed to power is much faster.
Fantastic. Thank you, Stephen. I'd like to move us forward a little bit to discuss energy parks and the future of power delivery, as we are seeing the power needs of the data center drastically rise. So, Mazen, if I can start with you, why has time to power become such a defining issue for AI infrastructure? And how are, perhaps you could tell us a little bit more about these localized energy parks and how they are helping operators to bypass lengthy utility interconnection timelines.
Yeah, thanks, Emma. I totally confirm this. It is a defining issue today. The main constraint for hyperscalers is no more land or capital or servers. It is time to power. So you can design and build the world most powerful data center in 18 months, but then you would need to wait 5 to 7 years to get power to that data center building. What are the main reasons behind this? I'll mention three. The first one is the growth level. So the growth of power demand level. So for decades, the grid worked because demand was growing predictably. So large loads coming from industry or from transportation and so on could be planned, sequenced, and integrated over time into the grid. But this assumption no longer holds today. Okay, so AI workloads are bringing sudden and massive changes in demand. We're talking about hundreds of gigawatts with load profiles that are different, and the grid is not engineered to absorb that fact quickly. And this mismatch, unfortunately, is structural and not temporary. That's the first reason. So growth level of demand. The second one is interconnection time, which is linked to a certain extent. So, for instance, in the US, the average utility interconnection wait time has gone to over 5 years. One example is PJM. So PJM Grid has a backlog of over 2,800 projects, and this is here I'm talking about the numbers of 2024, and this represents nearly 300 gigawatts of requested load that is sitting in line. Okay, so you can sense the size of the problem. The third is permitting. So permitting compounds even the problem, even more the problem. A new transmission line or substation upgrade would require environmental reviews, multi-agency approvals, community consultation, and so on and so on. And this can stretch from 3 to up to 10 years. I'll give another example here. Virginia, which is the world's largest data center market today. So Dominion Energy has warned operators that any new large load connection is simply not available before 2030. So that's to give you a bit of background of the problem. So energy parks came to flip this model entirely. So by co-locating power generation, which is basically gas turbines, solar storage, backup generation, and so on. So the power train. So by co-locating power generation directly or adjacent to the data center site, operators can connect behind the meter, bypassing the utility interconnections queue almost entirely. You can think of it like digging your own well instead of waiting to the city to extend the water network to your neighborhood. So energy parks allow energy users to secure their own power on their own terms, designed for their own load profiles and for their growth profile as well, because these clusters are adding up. And what can I add more on energy parks? Energy parks can operate independently from grid, and sometimes can act as a flexible participant to the grid and connect to the grid as well. And clearly here, many of the major hyperscalers, they have projects like this. They sign PPAs with IPPs that are building energy parks, and you can name it Microsoft, Google. We have examples of many of these guys.
Thanks, Mazen. And you mentioned there the powertrain, and I do have a question for you, Manav, which is when it comes to kind of the new standard for these powertrains, why is 800 VDC becoming the new standard, and what are the safety and efficiency benefits for operators in that regard?
Yeah, thanks for the question, Emma. So, with this AI inflection, right? It all starts from GPU. As I attributed earlier, the GPU power is growing from kilowatt to megawatt scale, right? So, what that means is to deliver high density power to the rack. If Stephen attributed earlier that the traditional way of delivering power is 54 volt DC to the rack, right? So you use a 480 or 400 volt AC in and 54 volt DC to the rack. Now, with the increased power requirement at the rack, what that results in your power equal to voltage times current simply, right? So if you keep your voltages lower, your currents are going to increase tremendously, and that increases losses, results in lower efficiency. So that's one of the drivers to move to higher voltage. If you move to higher voltage, it results in lower current, lower losses, and higher efficiency, right? So in essence, the 800 volt DC helps to cut the conductor size, helps with heating, and minimizes the energy losses. When we look at 800 volt DC, and again, some of these architectures, right, are in flux. We are working with a lot of partners and hyperscalers in the industry to design around it. So the way we think about this 800 volt DC system is we think about it from five perspective. One is 800 volt DC is not a single architecture. In fact, there is multiple variations of architecture which are possible. Uh, Number two is protection and selectivity should be considered as part of core design principles. Uh, Three is we consider that In order to fully integrate this system to deploy these safely, the viewpoint should be system over components, right? So the system level validation and design is extremely important. Number four is if you think about hyperscalers and these data center operators, they want to get assets which can be deployed at scale, which means that the supply chain and ecosystem needs to be ready to support this. And once these systems are deployed, you need a means to operate and maintain these assets, right? So just to come back, Emma, is the way we look at it is again, it's not one design. There's multiple paths, right? And there is multiple variations to address this. And I'll go into two dimensions which are commonly referred in the industry. One is the scale up, which means the number of tokens per watt or the density of power to be delivered to the rack is increasing. A few examples of this, right, which the industry and we have been working on, is a sidecar. Now, the sidecar, helps deliver today is about 600 kilowatt. The next generation could deliver up to 1.2 megawatt. So this helps with the increased density at the rack. Then there is other dimension called scale out. Now, scale out is a different problem to solve. So think about if a end user is trying to deploy a 200 megawatt or a 500 megawatt facility. Now they want to deploy this at scale, and that is a scale out. Right here is where this centralized DC, 800 volt DC comes into the picture. And again, with this, there is multiple variations, right? So if you think about the powertrain, which we discussed earlier, portions of the powertrain get replaced by new components, right? It starts with medium to low voltage conversion, new protection device, new control devices, right? So the system level integration is extremely critical. Also, to add, with these ultra high density clusters, there's two phenomena which are happening. One is, the loads are behaving differently, and what they exert back on the grid, it introduces new challenges, which is commonly known as load smoothing driven from load and fall right through in terms of what do we want to put back on the grid. So some of these, right, require intricate system design to fully understand and validate the system. Now, moving from that, there is another challenge which we need to kind of think about and we are addressing is the ecosystem readiness. So we'll start with safety and standards, right? The codes and standards. You think about UL, NFPA, IEEE, IC. Now, a lot of these, have been around for a while, but these have not been designed for direct current distribution, particularly for data centers. So some of these codes and standards, right, need to evolve primarily to address the safety, the interoperability, and resilience. Then once the codes and standards are available, there's another critical gap which needs to be addressed, which is associated with people who are going to be deploying, right? So you think about specifying engineers who help the end users write the project specification. Think about contractors, installers, etc. Right? Those people have not been exposed to deploying direct current distribution systems at scale. So a lot of upskilling is required. Now, your question about the DC safety, right? So, compared to alternate current, there is no zero crossing in DC. What that means is once an arc is initiated, it persists. So it requires a new philosophy for protection, faster interruption. At Schneider, right, we have tremendous experience in terms of the direct current systems, right? So again, the key here is that you cannot apply the AC thinking to the DC system. You need new protection philosophy, new ways to means to interrupt the current to deploy safety system. So again, just from to reiterate, the key points is think about system first, not the product first. Partner with someone who's got experience deploying these systems at scale. And let's not forget about the ecosystem readiness, right? Including the code and standard and getting the contractors, installers, other people sufficiently trained so these systems can be deployed at scale.
Perfect. Thanks so much, Manav. And speaking of deploying at scale, Mazen, perhaps you could spend a little bit of time going into more detail on kind of what differentiates an energy park from a more traditional data center campus.
Yeah, Emma, so uh, a traditional data center campus plugs into the utility grid like any office building or a factory. It takes power, it takes whatever power the grid delivers, pays the tariff, and hopes basically the utility keeps up with its growth, with the growth of that data center campus. While an energy park is more of a self-contained ecosystem, including generation, storage, transmission, compute, all planned and built from day one, or at least all planned from day one. Today, the scale of modern AI data centers makes the old model physically impossible. So we're talking here about AI campuses that can demand more than 1 gigawatt of power. 1 gigawatt of power can be compared to the output of a nuclear reactor. So one nuclear reactor, which is huge. And today, no utility substation is just sitting idle with a spare gigawatt waiting to be claimed. So clearly, behind the meter generation is no longer a preference. And for many operators, it's the only path to getting online at all. So that's mainly the difference. And you have other elements that an energy park brings. So time to power. So speed is one killer differentiator versus traditional campus. A behind the meter gas turbine or a modular power plant today can be permitted, installed, and energized in 24 up to 36 months. You compare that to a new utility substation or a transmission upgrade, which takes from 4 to 7 years. So for a hyperscaler competing in this AI arms race, this gap is really existential. So speed. Then on the operational side, operationally, an energy park gives the operator something traditional campuses don't give, which is power stability and full control over their energy stack. So power operators can decide on the fuel mix, the redundancy architecture, when to draw from storage versus generation, basically to guarantee the stability coming from the energy load fluctuations, and how to optimize their cost versus their carbon emissions. And consider it as the same difference between renting an apartment or owning the full building. So that's mainly the difference and differentiators of an energy park versus a data center campus, a traditional data center campus.
Thanks, Mazen. And when it comes to managing these energy parks, how are they? What is the role of? How is the role of software evolving? How are these becoming a software-defined energy system, as it were?
Software is key for these parks. The physical infrastructure of an energy park, so turbines, solar panels, batteries, cooling systems, UPSs, you name it, is really only half of the story. The real intelligence sits in the energy management system and the software that comes with, which an EMS acts basically like an air traffic control tower, continuously monitoring, controlling, and balancing supply and demand across every asset of the site, millisecond by millisecond. Think of it this way: without the software, an energy park is just a bunch of hardware, expensive bunch of hardware, I would say, and the EMS is what turns it into a living and breathing system. So examples: automatically spinning up a backup generator when a turbine trips offline, or drawing from battery storage when AI load fluctuates, and so on and so on. And with all this comes, pretty much big savings on the data for the data center operators. So these platforms are increasingly delivering predictive and autonomous operations rather than reactive actions to problems. So So modern EMS software forecast load demand based on the data center workload schedule, weather patterns in case of renewables, and EMS pre-positions resources accordingly for the operations of data centers. I want to mention interoperability as well, which is super important, and I guess we'll dedicate a question for that later on. Interoperability is really where the real value unlocks. An energy park might have different types of software. So inverter from one vendor, batteries from vendor B, gas turbines from vendor C, and so on and so on. And the EMS is the layer that should speak basically all of the protocols of these different vendors. And that's where interoperability plays an important role. EMS presents a single unified operational picture, bringing together all these different elements under one dashboard to control and monitor your energy park. So clearly, software plays an important role in there. It's not a simple topic, because it's a nascent topic, energy parks today and the link to data centers, but the right software started being there, and in my opinion, we need to build more to have a comprehensive solution in terms of when it comes to software to cover the full powertrain.
Yeah, thanks, Mazen. And when it comes to the sheer scalability of these facilities that we're seeing, we are seeing 5 gigawatt site plans. So how does the physical, as well as this, we've touched on kind of the software-defined energy system, but when it comes to the physical build process, how is this changing when you're effectively, building a small city's worth of power? If I can go to you for that one, Stephen.
Yeah, I would argue that's a large city's worth of power. 5 gigawatts is a lot of power. And, there's a couple of these planned, a few of these actually. And what we're seeing is a very, very high dependence on energy parks. It varies from plan to plan, but some of them are planning, 80% of their power are going to be from energy parks. So these 5 gigawatt sites are not going to be built all at once and flip the switch and it's on. These are going to take, probably many years, and they're going to be built in phases. Primarily because you can't get hundreds of thousands of electricians and HVAC technicians to put these all together. But the ones we're seeing are going to be built in chunks of, some of them are 50 megawatt chunks, some of them are 100, some are 150 megawatt chunks. So you want to align everything. You want to align the power systems, the energy park that's going to be feeding that specific chunk of the data center to be constructed and come online, when the physical, IT part of the data center is finished as well. So it's a tremendous coordination and planning process that's going on, and it's going to be rolled out into these phases that I talked about.
Fantastic. Thanks very much, Steve. I would like to move us forward a little bit, conscious of time, to discuss the digitalization, automation, and operational intelligence of these large-scale builds. So, Steve, turning it back to you, what digital tools are available to de-risk these large-scale builds using standardized reference architectures?
Yeah, it's very important. As I said, these are very, very complex builds, and to build these digitally and to run simulations is very important. We've actually digitized gigascale data centers in the Omniverse, and we're running our automation tools, our ETAP for the power systems, and Aviva on the cooling side. So you actually model these extensively before you build them in the physical world.
Yeah, absolutely. And Manav, when it comes to, Steve's talked about how we are able to de-risk these large-scale builds, but how are technologies like AI-powered monitoring and condition-based maintenance reducing operational risk inside the facility? And how does this enable failures to be predicted before they impact uptime?
Great question, Emma. So I'll start with Uptime, I mean, everyone understands what does an uptime mean for a data center customer, right? So the way we look at it is building the core capability to ensure that the system is up and running when it's intended to. It starts with understanding and collecting data to fully understand the state of the system, right? So we have ability to deploy and install thermal, electrical, mechanical sensors which drive continuous stream of data to our software suite EcoStructure, right? On EcoStructure, we can drive AI-driven analytics, right, which help understand what is the state of the system, which results in shifting from time-based maintenance or where unplanned maintenance happens to condition-based maintenance, right? So we fully understand what is the state of the system based upon data which is collected by these sensors in different assets, right? We do have a service called EcoCare, which is a tiered membership maintenance program, where our experts they monitor and assess the installations on a 24 by 7 basis. So an example would be right if there is a pre-pending failure occurring with potentially with UPS, the AI detects an anomaly. Our remote operating monitoring center kind of validates it, and we can send our service personnel out to the field to make sure that some of these problems are taken care of before they turn into something big, right? So think about it as a continuous service relationship that we can provide to these important end users, right? At the end of the day, what we combine is we monitor the assets, we leverage the AI insights by running our algorithms on top of it, and we provide an expert response, right? So if we have the data, we can drive the intelligence, and that can drive some actions. So from an outcome perspective, right, we believe that there could be 40% reduction in intrusive maintenance driven from some of these insights. It could reduce up to 75% in unplanned maintenance downtime, and it increases the availability by about 22%. In addition to the uptime, this also ties back to the safety, right? So the less manual interaction which you have with the electrical assets, there's fewer chances of R flash exposure even, right? So the shifts from reactive work to something which can be planned, de-energized, right? So it is it makes this extremely safe and also minimizes the downtime for these assets in field.
And when it comes to de-risking before deployment as well, how are technologies such as digital twins changing the way operators can design and validate AI infrastructure even before it's deployed?
Yeah, the great question again, right? So the way we and Stephen touched upon it briefly through attributing to ETAP and Viva. So the digital twin, we're looking into it from three aspects, right? One is the power modeling, second is the liquid modeling, and third is the airflow modeling. So what digital twin really means is a means to compress your cycle from the design to the operate phase, right? And a lot of it is enabled by means of dynamic simulation of a full system before the deployment, so you can validate de-risk some of these assets ahead of time. So I'll zoom in a little bit on the power modeling aspect, right? So with power modeling, right, we can use tools such as ETAP to accurately model real-time operating condition, fault scenarios, load transients. What do the harmonics look like? What is the protection system response, right? So think about it from like a design phase, right, where end user is designing the system along with a consultant, and they're laying out these one lines, so we can fully design and validate how the system may behave, driven from changes driven from sources or loads, like well, what does the air profile look like, right? Things like that. So we can fully validate the electrical characteristics of the system within the design phase. Now, when it comes to the forward phases like the construction phase, the testing phase, right? We can do a full protection and coordination studies across all scenarios, and we can simulate a lot of that ahead of time, right? So it enables arc flash analysis, right, and also reduces the commissioning time, which can be seen in the field. Once it goes to like deployment phase, it also offers a lot of flexibility, right? You can validate before implementing any changes. For instance, if an operator wants to change out some racks, there is some changes in the load, the dynamic system, the reconfiguration, right? In that event, right, a lot of that can be simulated right before a system gets deployed. So you can de-risk some of these, right? What the impact on the system is. So it again compresses a lot of the time to market, right? So again, it moves to advisory intelligence, right? Mode for a business.
Brilliant. Thank you, Manav. And Bazan, if I can turn it to you, we've talked a lot around software interoperability, but when it comes to that grid-to-chip architecture, how important is it that we have that software interoperability across the entire architecture ecosystem?
Yeah, look, that's part of the energy park story. So consider it as, grid to chip is the new supply chain for compute. An LLM training job doesn't depend mainly on GPUs. It depends in an energy park. Okay, it depends on a flawless chain that runs from electrons on the grid or the substation through transformers, UPS systems, cooling infrastructure, all the way down to the chip, to the compute. And a flaw or a break anywhere in that chain will cost millions to the operator. So interoperability is what enables and make that full chain visible end to end. And I just mentioned that previously. So an energy park might have hardware from different vendors, inverters from vendor A, batteries, BESS from another one, gas turbines from the turbine manufacturers, and UPS from, say, Schneider. And the EMS must speak the protocols of all these different equipments. Okay, Modbus, DNP3, etc. You name it. And the EMS must present a single unified operational picture. So operators will get one dashboard showing the health, economics, etc. of these 5 different vendor portals that don't talk to each other. So that's where interoperability plays a role. Without interoperability, you will get blind spots, which can be dangerous, or you would need to manage multi-systems, which can be risky for operators and inefficient at the same time. Overall, the industry is converging on open standards to solve these problems with DCIM software or the EMS platforms, which can ingest data from both the IT layers for DCIM or OT layer for the EMS. And clearly at Schneider, we're proudly at the forefront of this open standards trend.
Fantastic. Thank you, Mazen. Unfortunately, we are rapidly running out of time, so I will have to move us forward just to some final thoughts, kind of key takeaways, anything that you would like to leave our audience with as we kind of wrap this up. So, Stephen, maybe I can go to you for your final thoughts first.
Yes, thanks. No, the industry, is moving very fast. Great time to be in the data center industry. There's a lot of talk about power, but I think from this presentation, you've seen that there's innovation happening across the life cycle of design, on the simulation side, on the operation side, on the maintenance side, on the power generation side. So things are happening to support this AI race, and we're happy to be supporting it.
Absolutely. And Mazen, I'll go to you next.
Yeah, thank you, Emma, for hosting us. One comment on my side. This powertrain is large from the turbine down to the data center, and you don't find any player today that can cover it all. And at Schneider, we're present across different parts of that chain. And what I want to mention as well is that we're partnering with the different players of this value chain to be able to to tackle the different challenges that are coming from these AI loads fluctuations and so on. So the work is starting. I guess this trend is just starting, and happily we're pretty much well positioned to solve problems and to be an enabler for this trend.
Thank you very much, Mazen. And Manav, I'll let you have the last word if that's okay.
Yeah, thanks, Emma. So totally concur with what Stephen and Mazan talked about, right, in the closing narrative. So from my perspective, right, AI factories will be defined by one, power density, speed to deploy, and system reliability. So the key here is that the infrastructure needs to scale without failure, right? So it's a complex situation, right? A lot of industry, a lot of moving parts within the power density, speed to deploy, and system reliability. And Schneider can help with all of these three facets. Thank you, Emma.
Thank you so much. Well, unfortunately, will have to wrap it up there, but it's been a pleasure speaking with you, with the three of you. Thank you so much to Stephen, Mazen, and Manav for joining me. I really enjoyed the conversation. So thanks very much for giving up your time today.
Thanks, Emma.
Thank you very
Thank
much.
you.
Do check out the resources if you would like any further reading, and reach out to the speakers if you have any questions. I'm sure they'd be very happy to hear from you. Thank you, of course, to Schneider Electric for partnering with us on this episode, which will be available on demand shortly. Do stay tuned for the next episode, which will be coming up at the top of the hour. But until then, thank you so much to Stephen, Mazen, and Manav, and thank you to Schneider Electric.